Good evening, everyone. How are you all doing this evening? Hopefully, you're doing well. Hopefully, you've had a great day, great weekend, and all of that good old stuff. Um, as you can see, we're going to be discussing energy and power today. This is our last chapter. Good deal. Glad to hear it. Uh, this is our last chapter. So, again, there's no homework. I did assign a quiz. There's no journal. I believe I assigned a discussion board. And so that's all you have to do for this chapter. It's a quiz and a discussion board. So yes, Cassandra, yes. I think you got a lab experiment that you turned in this past weekend. You still have your project, obviously, and then you have a final coming up. I believe your project's due next Thursday or Friday. I think it's the 9th. I don't recall. It's the 9th or the 10th. But then your final is due the following week. Can I release the final lab 7th? What's that? What's due on the 7th? The project? Project due on the 7th? All right, good deal. Not sure what you mean about releasing the final lab though. For Javi. Is that Javi who said that? Oh no, that's Kelsey. Sorry. Oh, can I open it? Yeah, so the final lab was the series and I can't think right now. It was the series lab. It's not open, the final project. Thought I released that already. He did. Oh, so what do I need to release then? Is there anything that I need to release? Oh, are we straight? Yeah, your final lab was the oh, so you're saying you can't access the final project. Is that what you're saying? You should be able to access the final project, the launching device. It's open. It's been open. So yeah, it's open. Okay, cool, good deal. All right, so all right, good deal. Glad to hear it. So we got chapter 13. I'm gonna go through some of the energies today, and then I will finish it up on Thursday. So, Thursday will be your last lecture from me again. The next week, it'll just be open for if you have, you want to meet up for basically to discuss your project uh, or discuss things, I don't know, something on the final you may be curious about. But I'll be, like I said, I'll be on. More than likely, I'm going to be grading papers. So next week. Um, so I'll just sign in and I'll just leave it signed in. And somebody comes in, they want to talk, just ding me so I'll come and look and answer any questions you may have if you feel free to feel so. If you feel like you want to come in to our sessions and just talk about anything. So, but beyond that, you will not have to come into the sessions because we use the last week to work on projects when we're in class. And so I use those last 2 sessions for you to work on your project. All right. All right, cool. Let's jump into 13. What is energy? Now we've discussed power, right? We've discussed power. We've even discussed torque, right? But what is energy? What is energy? This is to get you to thinking, warm up your brain cells, if you have any. I'm just kidding. But yeah. So, not everybody at once. I know it's been a long day for you all. It's been a long day for myself. Uh, all out of those. Hey, I'm with you. I'm all out of it too. And I'm hanging on by a thread. uh, but man, I'm quite sure y'all all want to jump into this discussion though. Crawl into the finish line. Yeah, that's what we should do. We should just designate today for just like one-liners. Everybody would just give me their one-liner. I'm just kidding. I don't want to hear your one-liner. I don't want to read it either. No, but no, seriously. Energy. That's what we want to talk about. And the sooner we get through it, the better. Because we got some examples. I'm gonna have to go to the whiteboard, show y'all my artistry. Because I know y'all love seeing it. I know y'all love seeing the beautiful artwork that I paint on the whiteboard or scribble on the whiteboard. But either way, it's art, so it's abstract. Um, exactly. There you go, Mason. It's abstract. So, Lawson, thank you. Energy is like the output of an object. The output of an object. I like that. I like that. Energy is like the output of of an object. That's pretty good. Anybody else? What else do you think energy is? You get energy from fuel, right? So, like if you eat, food gives you energy to do something. So, what does that say? That energy is. Energy is power. Not quite power. Close, uh, but not quite. I like where you're going with it though. I like that. I like that motion. I like that. So I mean, really, you all you had to do is just Google it. But seeing that y'all don't really want to participate, aside from a handful of you that I appreciate your participation, you're gonna get 100 for today. Everybody else is zero. And there's no takebacks. So everybody's getting a zero that did participate. Everybody that participate getting 100. Thank you. And so, with that being said, now let's talk about energy. Energy, I like how it is defined here in Britannica. It states energy in physics, right? The capacity of doing work. So, Mason, from what you were saying, you was like energy is power. Not quite, but it's along that line, right? Energy is the capacity for doing work. It's the capacity. It's not doing work. It's the capacity, right? So when you get energy, you have the ability to do work, right? If you don't have the energy, then you do not have the ability to do work. It's like right now, right? Energy levels are low, so you don't really have the capacity or capability to have these discussions with me. So I shouldn't give y'all a zero. I get you. I hear you. I hear you. I do. And so therefore, I will not. I won't give you 100 either. I'm gonna give those people that participate. I'm just playing. I'm just kidding. I'm so silly. But anywho, energy in physics is the capacity of doing work, right? And it may exist in potential, kinetic, thermal, electrical, chemical, nuclear, and other various forms, right? And so when you're thinking about energy, I love this. When you're thinking about energy, keep this in mind. All forms of energy are associated with motion, right? So you think about thermal energy, right? You think about heat transferred, right? Heat transferred. You think about kinetic energy, it is the momentum of an object. You think about potential energy, you think about the potential this spring uh, could could load, or what load could be contracted from that spring, right? Because it is so stretched. So if that stretched spring is released, It's like there's a lot of energy that gets transferred from that spring. Um, and then you also have chemical and nuclear energy that you can get from nuclear, such as power, right? Meaning electricity, things like that. Nuclear energy can help you provide electricity, which is power, the capacity of doing work, right? Motion, even chemical reactions. But anyways, not to belabor those points. So what we're going to discuss today, you have various forms of energy, and we want to touch on kinetic energy. We want to touch on potential energy. We want to touch on thermal energy, but we'll start with my favorite, mechanical energy, right? Which obviously I say is my favorite because I'm a mechanical engineer. But mechanical energy, right? When you think about mechanical energy, you think about the work when it comes to moving objects, the energy it takes to move an object, the energy it takes for work to put in work to move an object, right? Making goods, processing food, even heating or cooling buildings, right? That takes some type of mechanical energy, right? Like a fan or an AC, air conditioning unit, right? Those are the things you think about when it comes to mechanical energy. So kinetic energy, like I was saying, is the first portion of this that I want to talk about when it comes to mechanical energy. And I know you all have seen this equation. So when work is done on or against an object, it changes the kinetic energy of the object. Right? Mechanical work is done by the engine, brings about a change in kinetic energy. And that work, which is equal to 1/2 mv squared minus, so the final velocity squared minus 1/2 mv, the m is the mass, times the initial velocity squared. That is your delta kinetic energy. All right. Of course, we're going to work some problems. And these are the units, obviously, of kinetic energy. All right. Kilogram mass squared per second squared. So when you're just keeping that in mind, what are the units for power? What are the units for power? Now, I know you know this. We've done this. We've worked problems with power before. Watt. And what is a watt? What is a watt? A watt is a watt. Y'all are funny. What is a watt? How do you get to a watt? A joule per second. There you go, Mason. I was hoping you would give it to me because you said where energy was power, right? And so it takes energy to get power, right? So a watt is a joule per second. So a watt is the measure of energy over a period of time. I mean, power is the measure of energy over a period of time. All right. So let's look at an example when it comes to mechanical energy. Pretty easy stuff, obviously. If I can find an example, of course. Let's look at example 13.1. All right. Example 13.1. So let's go to the whiteboard. Yay. I didn't get a round of applause. I did not get a round of applause. So I'll read it. Example 13.1, and if you're in the 5th edition, that's on page 435. It says determine the net force needed to bring a car that is traveling at 90 kilometers per hour to a full stop in a distance of 100 meters. All right, so you got this car. Uh-oh, I'm about to make an attempt. Yep, yeah, I am. Oh, goodness. No, he did it. Yes, he is. He is actually drawing a car or some rendition of a car. That's the bumper, folks. And that's a long chassis. Anywho, oh man, those are some little small rims. Hey, it's a low profile. Those are low profile tires. It's low riding. They're low riding. Not really low because it's almost like they're on the brake disc. But anywho, let's put a window in there. It's a coupe. It's a coupe. Let's get us a door handle. Oh man, they're gonna go the powers that be are gonna watch this thing and be like, Corey, it's hard to learn anything from your class because you were drawing pictures. It's like, no, no, no. The pictures are a necessity. It's some kind of coupe. Uh, don't mind the door. This is it's okay. It's okay. That's we got some kind of grill. We just put something up there for the grill. Some effects for the grill. Let's put a little emblem up here. I don't know what it's gonna be, but let's give it some like little shape. Man, it looks like a bird. I like it. That's cool. We low riding with a bird emblem on the hood of our car. All right, let's put a little person in there. Oh, it's example. It's example 13.1. Yeah, it's the example. All right, so we got a little person in there. I don't know if that looks like a person or not. But for the initial velocity V1 is equal to 90 kilometers per hour. All right. And so what we're trying to determine is the force it will take for um, basically hitting the brakes. How much force would it take to bring this car to a complete stop? All right. If it's traveling at this rate and it goes a distance of 100 meters, right? Then what is the force? But first, we got to what before we calculate the force, we have to calculate what the kinetic energy. All right. So to do that, we know the mass, correct? The mass is 1,400 kilograms. So delta KE is equal to mass times V2 squared over 2 minus mass times V1 squared over 2. What's V2? We know what the mass is. What's V2? Nobody knows? We know what V1 is. What's V2? How do we calculate V2? Or do we need to? Oh man, everybody's dead tonight. Dead sleep, dead tired. Well, that's okay. We only have an hour and 30 minutes to go. So I'll wait. I will wait. Oh, Mason, she's thinking, okay. Well, go ahead. You got time. You got an hour and 34 minutes and counting. I'll wait. Let me know when you're ready. Man, so what are y'all gonna be eating for dinner while we wait? Up. Speed at position 2, correct. Yes, it's the final velocity. There you go. V2. Yay. All right, we can move on. We can move on. V2 is 0. Thanks, Hunter. So then, we got 0 here. Oh, yeah, okay. Yeah, we had pizza at work. They brought us pizza because we were there for so long. I just actually got home like 10 minutes ago. No, I'm kidding. I got home like 30 minutes ago. Man, they brought Domino's. I wasn't too thrilled. But I ate it. Cool. So Sahil says negative 6,300, 63,000. Wait. All right. So you got 90 squared, right? Times the mass, which is 1,400. What are the units? 1,400 kilograms over 2 times 90. All right. And so what that'll be is kilometers or kilometers squared over hours squared. Right? And so if you were to multiply 700 times 90 squared, all right, you get, what is that? 5,670,000 kilometers squared, kilogram per hour squared. So what is this in meters per second squared? If I were to convert that to meters per second. Meters squared per second squared, rather. So kilogram meter squared per second squared. So Hunter, you just wrote out that I guess 90 kilometers per hour is 25 meters per second. Is that correct? All right, so cool. That makes life easier, right? So if you put 25 meters per second square in here, right where I have the 90, then you'll get 25 squared times 700. You get 437,500 kilogram meter squared per second squared. Is that what you all got? So I got 437,500 meter squared, kilogram meter squared per second squared. Is that what you all got? That's a 5. So 500. All right, good deal. So now that we've calculated the energy, what do we need to do to calculate the force? And remember, the units for force is kilograms, meters per second squared. So what do we need to do to calculate the force? So if you all recall, work is equal to force times distance. Work is equal to force times distance. So that would mean work is energy? Wait, what? I thought energy was the capacity to do work. So how is work synonymous to energy? Right? Well, right. So with that being said, you have kinetic energy, you have potential energy. No worries. It's okay. So you have kinetic energy, which is work in motion. Then you have potential energy, which is work loaded up. It's like the work you haven't done yet, but it's loaded up. That's interesting. It's an interesting concept when you think about it, right? Um, wherein you need energy to do work, but then work is synonymous with energy in regards to not how it's derived, but similarly it is, right? But not because kinetic energy isn't force times distance, but you can use force times distance to calculate to solve for the force when you solve for the energy that you have derived from the work that was done on the car. I know it's like a circle It's so interesting. Like, why would they use the concept of work and energy, wherein if they have the same units? It's the same, like it's momentum. It's like a different type of energy. It's a different form of it. When you think about a load being applied over a distance versus kinetic energy, which is the mass times the velocity squared. I know it's so interesting. But this is just an intro class. So when you guys get into thermodynamics and you in your higher level chemical engineering class and mechanical and all of that stuff, then you'll get a more theoretical response as of why. But for this class, all you need to know is work and energy are synonymous. So with that being said, to solve for F, all you need to do is divide your kinetic energy by the distance. And so what does that give you? You just move the decimal place over 2 times. No, there it is. Thanks, Hunter. Negative 4375. That's a pretty good problem. Absolutely. Negative because it's slowing down. Somebody's been taking physics. There's that vector, that direction. Oh, you haven't taken it yet? Okay. Did you take it in high school? Oh, okay. All right, all right. It's just that knowledge there. Good deal. Somebody's been reading. Well, back to the lecture at hand. So that's kinetic energy. Any questions on kinetic energy? So potential energy is always interesting, right? Interesting in how it's defined, interesting because it hasn't happened yet. It's more or less you're trying to determine, you know what's interesting also when I think about potential energy, why are we studying something that has potential but it hasn't happened? Well, reason being is because of safety parameters, right? Because if you're using a spring, like however many know you got a spring loaded, um, you got this loaded spring rather on your garage door, and it could be a projectile. So when you think about elevating and then lowering your garage, if you stay in a house with a garage or what have you, I mean that could be dangerous. So when you think about potential energy, you think about putting in parameters to prevent it from being converted into kinetic energy, right? And so when I was in, undergrad, or even when I was in physics in high school, how we would look at this, we would look at potential energy being converted into kinetic energy. And there will be cases where you will have problems where you're looking at the potential energy and then how it would change into kinetic energy if movement took place, right? And so then you would have to take into account the potential energy and then add that to the kinetic energy after it changed, right? That's being if you do the velocity and all of those things, correct? But with that being said, with that spring that you have on your garage door, you want to put in safety parameters to prevent it from being converted into kinetic energy. So that's why potential energy, determining potential energy is so important, right? For safety, right? Because you don't want anybody around, or even when you think about like a bomb, uh, when you're determining a chemical reaction and the explosion that could occur, right? You want to put in a blast radius, all right? So if you only want to destroy the people that you dropping that bomb on, I know that was a bad. I think Hunter has a better example, but I'm gonna go with my bomb analogy. If you want to, drop this bomb on somebody, you want to make sure you're far enough away that you don't blow yourself up. So that's why potential energy is important. So, and then Hunter said it's like I like to imagine car tires exploding when people uh, overfill them for potential to kinetic. Absolutely, right? Because there's this range, so you want to set a limit. When your manufacturer says the limit on your tires are 35 psi gauge for each tire, then you need to mind that, because if you don't want to fill that thing to the point where you blow it up, right? And your potential turns into kinetic. And then you have projectiles, things of that nature. Imagine a balloon, right? But anywho, so potential energy, this is how it's defined here. It's defined as the gravitational potential energy represents the amount of work required to lift an object with a mass m through a vertical distance, right? And that's how it's defined more or less in your book. All right. So let me bring up my article. I like the way they define stuff. Let's see. So potential kinetic energy, for example, if any given body has kinetic energy, if it is in motion, a tension device such as a bow or spring, though at rest, has the potential for creating motion. It contains potential energy because of its configuration. Similarly, nuclear energy is potential energy because it results from the configuration of a subatomic particles in the nucleus of an atom. All right. So if you think about potential, you think about a tension device or a spring. Though it is at rest, it has potential of creating motion. So that's how you want to look at potential energy. It has potential. It is a device or an object that is at rest that has potential for creating motion. Right? That's where the bomb analogy comes in. All right. So they are looking at it from this standpoint because of the way it is defined. It's mass times gravity times the differential of height. All right. Because if you have it at a certain level, then it drops, then it becomes kinetic. All right. Then it goes back to rest though. But because it's at this height, right? If it were to go into motion, now it is in kinetic energy because it can fall at any moment. All right. And I won't do an example on a potential energy. That should be pretty self-explanatory. I will do an example, however. Let's see. No. Yeah, let's do that example. On elastic energy. Because elastic energy is a little bit more interesting. All right, so when a spring is stretched, and elastic energy is interesting because it's pretty much like potential energy, but they're using the spring constant. They're using the spring energy K form, and then your deflection or your displacement X to solve for elastic energy. All right. When a spring is stretched or compressed from its unstretched position, elastic energy is stored in the spring, right? which is still potential energy. All right. Energy will be released when the spring is allowed, turns into kinetic energy to return to its unstretched position. All right. So elastic energy stored in the spring is given by such. Now, I know you all remember when I started working on a problem such as this. Well, maybe you don't, but it's okay. It's okay because we're about to do one now. So you have your surface, you have your spring, and then you have this force being applied to the spring, right? And then it makes basically it pulls it, right? Stretches out that spring. And so what ends up happening is the spring goes from there to there, and that's your X. So if we knew F, then we could solve for K. If we knew F and K, then we could solve for X. So if we were to do example 13.3, right, it says the unstretched, I'll read it. So it says determine the change in the elastic energy of the spring shown in figure 13.6 when it is stretched from A, position 1, to position 2, B, position 2, to position 3, and position 1 to position 3. The spring constant K is 100 newtons per centimeter. Now, the question is, we need to determine the change in elastic energy of this spring shown. All right, so we know the formula. It is 1/2 K X squared. So from position 1 to position 2, it's 0 to 5 centimeters. So that should be pretty easy. So delta EE is equal to what? So if position 1 to 2 is equal to 5 centimeters, and then we said 1/2 K times X 2 squared minus X 1 squared. Then double E is equal to what? Because we know what position 1 is. We already said it's 0. So then you plug in your 5 centimeters or 0.05 meters, right? And from position 1 to position 2, what would be the answer? For double E. Oh, we're playing that waiting game again? All right, well, we got an hour and 11 minutes till 10, so y'all let me know whenever y'all are ready. Man, I'm looking forward to eating dinner. I guess for those of you that have eaten dinner, I guess you're not. But but I'm looking forward to it. All right, no worries. So we got double E, right? Elastic energy. Uh, so elastic energy is 1/2 K times X squared. Now, what is K? We know what K is. They gave it to us. What is K? You're looking at example 13.3. I'll give it to you. K is 100. Yes, that's the spring constant. K is 100 newtons per centimeter. All right. So what is the elastic energy here? Delta EE is equal to what? There it is, 12.5 joules. And so you would basically solve the remaining positions just like that. All right. All right. So let's go back to lecture. See what we got next. Because I don't want to talk about conservation of energy until next class. So you may be done. So you got thermal energy, which you all remember thermal energy. We got 3 modes of heat transfer: conduction, convection, and radiation. So we've gone over that. Gone over the units. All right. So conservation of energy, conservation of mechanical energy. We will talk about conservation of mechanical energy on Thursday. All right. So I know you all have been ready to get off. So here's your chance. But before you go, do you have any questions? Do you have any questions? All right, good deal. So the project is going to be like a lab report. So, and then I believe I told you to use the 8 steps of design when you're looking at writing your report. So it'll be in paragraph form. I don't need bullet points and listing. You will not get a good grade if you do that. So just write it in paragraph form, elaborating and answering the questions that are posed. So this is the first time I am doing this project. So this week you only have a quiz and a discussion board. Discussion is pretty cool. I think it was really cool. But I don't have an example of this project because it's the first time I'm doing it. Usually we do a different project for our final project. And I decided I wanted to do a different project this semester. So, and if you know, you guys do a good job, I might introduce it again next semester. If you don't, then I might go back to the old project. No, I'm just playing. I think I like this project. So if we're not in class in the fall, then more than likely I'm going to come back to this project. We are in the class in the fall, then I'll go back to the initial project, which was building a launching device. Building a launching device was probably cooler than writing a report on it. But we're still in COVID season. Not in Texas. I forgot. Maybe I should have did it. Nah, I'm just kidding. Maybe I should have. Maybe I should have just had y'all all build a launcher device, and then we could have tested it on campus. Nah, not really. They wouldn't let us on. Oh man, yeah, it's actually really cool, man. I had a couple uh classes do it. Yeah, they built their launching device. Then we go outside and we launch it, and we see how far everybody's everybody's device gets launched. Well, the projectile gets launched, and then we measure it. So, there you go, A1 builder. Hopefully, you got A1 designer because we had a few people that didn't make the launching distance. There was actually a set launching distance your device has to launch to. But yeah, I'm letting you guys define that for the report. Okay, Lawson. Lightweight. Got you. Got you. I might just have your group go ahead and build it and design it and build it, and then give me your launching parameters based on what they should be. I might just do that. And you only got 2 weeks though. Yeah, yeah, but you couldn't use steel though, honey. You had to use wood. So there were limitations. I know there were constraints rather. Pencil and rubber bands. Oh man, you sound so confident. That's funny. I wish you could have been in my class in a few semesters ago. That would have been cool. But anywho, I will not hold you guys, ladies and gentlemen, any longer.